So, Marcus, we can start, right?
1 second.
I don't know if it's needed to introduce Isabel again.
No, you can start.
But we should. So, well, I guess most of you have already met Isabel yesterday, and many of you will see her later for lunch. So that time only is confirmed. So Isabel is she's an expert on galaxies and AGN in particular. She's from Badajoz, right? But has been working for many years now in Granada. So she's a deputy director of the IAA, the Instituto de Astrofísica de Andalucía in Granada, and science director of the Severo Ochoa of the IAA. And well, as we heard also yesterday, she's very active in many other things, in particular equality issues. But today is more on science, right? So welcome. Thanks, Isabel.
Thank you. Good morning. Thank you very much for being here. Today, as you know, I'm talking about the presence and impact of outflows at the lowest level of nuclear activity. I'll try to explain everything I'm going to talk about. So, even
sorry, if you want, you can remove your mask. It's up to you.
If you don't mind?
No.
No, it's fine.
You're here. It's much better like this, right? So, within the title of many terms that I'd like to explain more or less during the talk. So I'm talking about outflows. I will tell you what it is and what it is important. I'll talk about the nuclear activity in galaxies. I hope I won't need to explain what a galaxy is, I guess. So, but what nuclear activity is, or what we consider to be active galactic nuclei, and also I will be focused. I'll focus my talk in the lowest end of the power of the AGN, of the active galactic nuclei in galaxies, with a kind of special kind of galaxies that you will see later on. All what I'm showing today is, of course, as everything I've done in research in collaboration with a number of people. And here you have the list of the main collaborators from what I'm going to show today, who are Laura Hermosa, who is making his PhD with us, Sara Cazzoli, a postdoc, Josefa Masegosa, senior researcher at the IAA, Omaira González Martín, who has a permanent position in Mexico, and Lorena Hernandez Garcia, who made also the thesis as well as Omaira with us, and now is in Chile. So what you see here in this first transparency is an HST image of one of these galaxies about what I'm going to talk. That is NGC1052, and this is a central part where you see the dust lanes and everything, the bright bulge in the center. And in these other two plots, you see the same galaxy, but here you have a much better view of the central region. You see those are the same dust lanes here. And where you can see, I don't know where you see here, but this is an amplified view of the central part. What you see here, this is in H alpha. What I'm talking about, it's a kind of outflow. This is a LINER galaxy. You will see what a LINER galaxy is later on. And this is a tiny outflow. You see that the whole galaxy is much bigger than this image. And this is the size of what I'm talking about in this case. But you will see that there are many cases in which these outflows in low luminosity AGNs are much more important. And they are expected to be huge for high power AGNs, starting from quasars, where you see outflows with a high power, and going down to ciffers. So this is the outline of the talk. And here you see an image of an active galaxy. It is NGC1068. In fact, it's a cipher where this is a composition of this is an ideal view of what we expect to have at the center of a galaxy. In fact, in the AGN will be bright here, so the accretion disk towards the supermassive black hole is inside these obscuring torus, which is a kind of a donut. So we will see how this structure is important to to deal with nuclear activity and to explain the different classes. And so first of all, I'll tell you about what an active galaxy is, going a little bit back in history to better understand what we are dealing with. Then I'll briefly talk about the unified model that considers this structure to explain how we see the different classes of AGNs. Also a little bit about supermassive black holes in the centers of galaxies, and connecting what it was before an active galaxy. The term of an active galaxy as what is changing to more when is a galaxy, when a galaxy is active. You'll see why. Then I explain what liners are and at the lowest end of the AGN activity. And then I'll focus the remaining of the talk on talking about the outflows in these liners galaxies. From low-slit spectroscopy, these are the works in our group. From a particular study with integral field spectroscopy, and also for imaging of the ionized gas, and then the conclusions at the end. So first of all, what is an active galaxy? An active galaxy is a galaxy that hosts an active galactic nucleus. So you will, so what is an active galactic nucleus? An active galactic nucleus is a compact region at the center of a galaxy that has a luminosity which is much, what is it? Much higher than normal in the central region, and with characteristics that indicate that the processes that are producing that luminosity in the different frequencies, it means that the stars cannot produce such spectral energy distributions and spectral characteristics. So they are characterized, this very central region, by having non-stellar emission at all frequencies, from radio to microwave, infrared, optical, ultraviolet, X-rays, and gamma rays. And these emissions are thought to be produced by the accretion of matter by a supermassive black hole in the center. So just to tell you a little bit about the history, active galaxies, in fact, quasars, are as old as I am, or maybe I am as old as the discoveries of quasars. So it's not that old, I would like to say. And they were first discovered with observations in the visible. In fact, in 1909, there was in the 67, the quasars, not 1901, I know that old. Okay, so the first things to be discovered was that there was peculiar emission lines in NGC 1068. In the spectrum of the central part, there were weird emission lines there that nobody knew how to identify. Then in 1943, Carl Siffert studied a kind of galaxies that had a very, very bright nucleus, and that seemed to be connected like these ones. NGC 1068 was one of those. That's what then later on we call them Siffert galaxies. Okay, and in fact, it was also discovered that there was a class of weird stars, so unresolved sources that were very bright in radio frequencies, that were called quasars, because they were very, very bright. They were unresolved, so they seemed to be stars, but with somewhat peculiar properties. So a kind of, strange properties to be stars. And in fact, in 1963, Malcolm Smith measured the redshift of 3C273, that it was one of those weird stars, and the redshift told us that it had an enormous luminosity because it was very far away from us. It was, in fact, not a star. This is an HST image of this object, of 3C273, where you can see that it's very bright. It seems to be a star. You can see a jet here as well. And in fact, there was a controversy already in the 90s that you're probably not aware about. And it was that, well, first thing is just what I was saying. This is a star. This is a big star with the absorption lines in the spectrum. You can see that gamma, H beta, H alpha, and then this quasar in which they realized that the emission lines were corresponding to the same base absorption lines here in the star. So remaining that implying that the redshift was 0.16. So very, very far away from us. Okay. So as I was saying, there was a controversy in the 90s, just before the study of the images of quasars with HST, because people thought that there may be quasars that were called as being naked. So there was just a central region with no galaxy around. And in fact, thanks to the HST, the Hubble Space Telescope, we could have a very, precious spatial resolution images that showed that in fact, underneath every of those quasars, there was a galaxy. And you can see that also very good in 3C to 73 with a coronagraph, where even if in the direct image, you see nothing. When you put a coronagraph, you see perfectly well the galaxy that is. Yes.
What's a coronagraph? What is a coronagraph?
It's an instrument that blocks the luminosity coming from the center. It's the same kind of thing that you put when you're observing the sun. And so you block the central because otherwise it's saturated because of the big luminosity. And it allows you to observe, to take rid of the central contaminating source and then observe the things around, because otherwise you saturate everything. Okay, so it was resolved in the 90s that in fact, quasars as well were active galaxies, having a very, very high power active galactic nucleus in the center. So what about the unified model? In fact, along all these years, there were, discoveries of kind of a taxonomy of the different galaxies hosting AGNs that were called blazars on Seyfert's narrow line radio galaxies and so on. So finally, starting in 95, Meguri and Padovani designed a kind of a model, of a cartoon model, in fact, what told us that in the central region of a galaxy, you had this obscuring structure that was much more beautifully shown here. This is the absorbing structure, which is called the torus, normally. And then you have, within the torus, you have a very high velocities region, which is called the broadline regions, because when you have the view through that those clouds, you have very, very wide emission lines. So those are quasars, for instance, and Seyfert ones. And when you look through the torus itself, you don't have access to this region where the very high velocities are taking place. And then you only see this region, because this is unresolved, it's a very tiny region, and you see just the narrow emission line regions. This is a much more recent, and I don't have a laser anymore, but anyway, here it's a much more elaborated, here it is, version, when you can see that you have mainly two groups, the radio loud and the radio quiets. And depending on the orientation of the line of sight with respect to this central region, you can say that you have one object or the other. So all of them are the same things, but it mainly depends on the orientation of your line of sight with respect to this central structure. In fact, it depends on the orientation, but also on the, you have two groups. We don't know yet, understand why some of them host radio jets and others don't. So you have the orientation, but also there's a kind of dependency with a degree of obscuration by dust. When you have much more dust, it's much more difficult, even dust within the host galaxy, not the torus itself. So it's much more complicated than this, but it's a kind of a general view. And in the recent years, it has been also found that there is a kind of dependency also with the mass of a central black hole, and also with the accretion rate of matter into the supermassive black holes. So, so another thing that has been discovered just starting in this century is that there is a kind of very good relationship between the black hole mass, so the mass of the supermassive black hole, the central supermassive black holes, and the mass of a central bulge in any galaxy irrespectively of if it is active or not. So in any galaxy of at least the kind of our own galaxy, so the Milky Way and bigger galaxies, and even in some smaller ones as well, we have a correlation between the mass of the central bulge and the mass of a supermassive black hole that it is in the center. It's a positive correlation. So the higher the central mass of the bulge is, the higher the mass of the supermassive black hole. And it seems to be an intrinsic relationship that it's showing that these two parameters being related, it means that there's something to do with the co-evolution of the supermassive black hole and the galaxy itself. Yes.
So the mass of the supermassive black hole is computed from the broadness of the lines there, or how is inferred? The usual way to infer the supermassive.
For active galaxies, you can measure it from the width of the lines in the broad line regions. But when the galaxy is not active, you cannot use that, of course, because you don't have broad lines. So what you use is just to try to infer the mass of the central region with the spectroscopy. So, I mean, through, for instance, ST's HST spectroscopy, you can resolve the very central regions of the galaxies, and from the velocity dispersion of the amplitude of the rotation curve, you can measure the central mass, which in fact is is so close to the center that it cannot be explained otherwise than with the supermassive black hole. Good. So that's why I was saying at the beginning that in the outline, we are some kind of changing from what is an active galaxy to when a galaxy is active. Because we know at the very beginning of these studies, people thought that active galaxies were completely different from non-active galaxies. But what we tend to think of nowadays is that since all galaxies of this kind host supermassive black holes, and we find not so big differences between active and inactive galaxies, it may be that it's something related to the life of the galaxy and to when the matter is available for the supermassive black hole to be fed and to show all the special properties that active galaxies shows. And these are a simulation by Hopkins, sorry I didn't put a reference, in which you see how the Eddington ratio changes along the life of the galaxy. In fact, being able to explain why a galaxy could be normal in some periods and could be active galaxies in some others. So that's what I'm referring to when we talk to when a galaxy is active. In fact, these processes can take place many times during the lifetime of the same galaxy, depending on the viability of matter to be given to the supermassive black hole, and also the mechanisms that allow the matter to be transported to the center. So what are LINERs? LINERs are a specific class of active galactic nuclei, which are the lowest, have the lowest power in the central regions. And they are special because of some other properties. In fact, they were classified first in 1980 by Heckman, based on the properties of the optical spectra. And here you see, I don't know if you're used to having to face two optical spectra of galaxies. So this is an optical spectra. So here you have the wavelength from 4,000 to 6,500 angstroms. So this is in the optical, and this is the relative intensity. So here you can see on the bottom, you see what we call an H2 galaxy, which is a star-forming galaxy. In fact, what we don't see here the continuum from the stars. We just see the emission lines that are produced by the gas being ionized, and that's mainly. So here you see H alpha. So Bellman law is H alpha and H beta here, and it's delta gamma. And then you see also the forbidden lines of nitrogen here around H alpha and sulfur. And here you see oxygen 3 and oxygen 1. Oxygen 1 should be here. So there are lines, emission lines produced by the gas being ionized by some process. In these kind of galaxies, it is because of stars, young stars, which are very massive. And here is you see a spectrum of a Seyfert. Here you see the absorption lines that come from the stellar population of the host. In a quasar, you normally don't see that because the nucleus itself is so bright that it overwhelms all the rest of luminosity. And here you see the same kind of emission lines. And this is a LINER galaxy. And this is to show that LINERs are called low ionization, narrow emitting, nuclear emitting regions. So it means that the low ionization, so the oxygen 1, which is here, oxygen 1 lines are very bright with respect to higher ionization lines as, for instance, nitrogen 2, sulfur 2, or oxygen 3. So in fact, from the very beginning already Hegman showed that normally LINERs are hosted by early type galaxies. They are much less luminous than Seyferts, and there's a kind of a continuity in the properties that you can measure considering the line ratios in the spectroscopy. But since the nuclei are much fainter, it's difficult to measure the properties because there's a huge contamination from the host galaxy itself. And I'll tell you more about this problem. And since the very beginning in the 80s already, there was a connection with the nuclear activity. In fact, when we use the lines ratios, these are plots using oxygen 3 over H beta and nitrogen 2 over H alpha. This is sulfur 2, and this is oxygen 1. We can know what kind of nucleus we have because of these ratios. That's because models explain that these ratios can be explained by star formation. So the H2 galaxies, so these orange galaxies here, these are the so-called BPT diagrams. I'm sure you are aware of, some of you are aware of those. And in red, you see the what we call the Seyferts, and in the blue, the square blues are the LINER galaxies, that's some kind of composites in the triangles. And so when you put models on top of these observations to try to explain these line ratios, you find that for these regions, so the region occupied by LINERs, they can be explained either by non-stellar photoionization, as it is for Seyferts, or by shocks, or by post-AGB stars. So you have to use several strategies to disentangle what is the actual process taking place, to be sure that you're dealing with an AGN, okay? For instance, if you see broad lines, H alpha or H beta broad lines, permitted lines, you're sure that you have an AGN because you're having direct look to the broad line region. But if you have just narrow lines, then you don't know. But there are other frequencies in which you can have a look and better disentangle, as I'll show you later. In fact, LINERs are the most numerous AGN population in the universe, in the local universe. So these are very important because they are, firstly, they are the step connecting more active galaxies, more active AGNs with normal galaxies, and also because they are the most frequent population. So most of the properties that, I mean, they give us a lot the opportunity of knowing much better in a statistically large samples of what active galaxies are, at least in these low power galaxies, AGNs. These are some examples of LINERs, normally hosted by early type galaxies, either ellipticals or lenticulars, in some Seyfert as well, but with big bulges. And here you see some other examples of different active galaxies, a Seyfert 1 in which you see the broad lines. You see the very broad lines here. A Seyfert 2 in which you see through the torus, so you don't see the broad lines here. And this is a spectrum of a mean quasar, a BLAC, I mean, of all of the objects I have been talking about. So coming back to the nucleuses of LINERs, we made a study in 2009 related to, I mean, trying to relate other frequencies to the point of knowing whether an active galactic nucleus was, in fact, what explained the properties of some LINERs. So we took all the Chandra images from a sample of 82 galaxies, and we classified the morphology that they had. These are the different bands in X-rays. And this is the optical, but I mean, with a kind of treatment. And this is the infrared. And so here, just for you to know, here is the hard X-ray band. So we classified the objects in those which had an unresolved nuclear source at the hard X-rays or didn't have that. So the sample could be separated in two classes, what we called AGN candidates which were the 60% and the non-AGN candidates, because we expect an AGN. If we have an AGN, we expect to have those kind of unresolved had X-rays. In fact, if we used another, radio frequencies and other wavelengths, we ended up with concluding that 90% of the 82 LINER galaxies were hosting an AGN. So in fact, we are sure that at least these 90% galaxies are, the nuclear source is produced by an active galactic nucleus, which is important in order not to mix up with other processes. And another thing that we did in 2018 was to analyze all the HST images of the galaxies in that 82 galaxy sample, having narrow band images in HST that were centered in the H alpha emission, so just tracing the ionized gas in the very central regions, and we analyzed the morphology. We studied a total of 32 liners, and we concluded that most of them, 65%, show either core-low morphologies or outflow candidate morphology. This is the NGC1052, so the galaxy that I showed in the very first transparency, and this is the kind of outflow you see in the very central regions. These are 5 or seconds. And but in fact, these are images, so we don't know if what we are saying are outflows or not. And why outflows are important? Outflows in the last decade or so have been used recursively to try to explain this kind of relation I showed you between the massive central black hole and the massive central galaxy, because they are helping in feedback processes, both positive and negative, in terms of inhibiting or enhancing star formation in the central parts. And outflows are very important. Yes?
So the outflows that you see in these 8 LINER AGN populations, I understand that they come from some nuclear activity, but are there some cases of non-liners that you classified as non-EGNs that present the outflows, or in those cases you cannot see outflows? Like,
there are very few of them, but in fact we also know that star formation, strong star formation activity may produce as well outflows. So the point here in liners is to try to first to look for outflows, and then to try to understand what process is causing the outflow itself. And since LINER galaxies normally don't have a lot of star formation, we don't expect stars being able to produce the outflow. So it has to be the AGN or something else, or something related to the AGN itself, as we will see. Okay. So, so in general, outflows are very important for a very high power AGNs. For instance, for quasars, there are a lot of studies with the spectroscopy showing the presence of very broad and blue shifted lines that only can be explained invoking the presence of outflows. And there's also there are also some studies showing that this seems to be related to the power of the AGN itself, in the sense that Seyfert galaxies, which are less powerful than quasars, having less powerful outflows. But for liners, which is as I told you, it is the most frequent population of AGNs, we don't know. We don't know because there are many complications, because they are less powerful, of course, to study. And there are not many, there are not many studies in general, just individual cases. And just we started doing a kind of a study considering spectroscopy, because imaging is not enough, as I showed. And these are these 2 works here that I'm trying to wrap up in 1 or 2 transparencies. I'm not sure. So here again is the case of NGC 4438 that we are studying with IFU. IFU is integral field spectroscopy. So I will tell you what it is in a minute, but I don't have the results yet. But I'll talk about a specific case, a different one. So what we did, just using spectroscopy, so to know the kinematics and to be sure that we had outflows, not just the morphology of the ionized gas doing whatever. We analyzed a total of 31 liners from type 1, meaning that they had broad lines, and type 2, meaning that they hadn't, in these two papers. And what we did, which we had this kind of information. For instance, this is the spectrum taken with the 3.5 meter telescope in Calar Alto, in the region between oxygen 1 and sulfur 2. So you see these emission lines. And also we used the HST spectra that were very useful because they are obtained in a much smaller region, because HST has a brilliant spatial resolution. So this corresponds to region much more closer to the center. And in fact, from the comparison of these two, you see that in the central region, we see very clearly the broad lines in this case that we don't see when we are dealing with a higher region, because let's imagine that with the Caja, you are focusing in a region this size. So you take the nucleus, but also the rest of the host galaxy. And with HST, you are much closer to the center, so the contamination from the host is much smaller. So you're able to see much better the presence of the broadband regions. What we did,
Isabel,
yes?
are there any ways to actually mask the outside part?
To mask?
Yes, somehow take the spectral of the center. I mean, sorry, if you have IFU, you can do it, right?
Yeah.
So then how?
But you do it, I mean, what you do when you put spectrum, a long slit spectrum. So you put the slits over your galaxy, and then you are going to have one spectrum per position in your galaxy. So you go from the outskirts. Imagine that you have the center here of your galaxy, and the long slit goes through this way. So you are going from this region where you have spectrum of the outskirts, and then you are approaching the center. Then you will have the spectrum of the center, and then you will have again the other way around.
Right.
So here I'm showing you the spectrum of the central region.
Okay, so because you mentioned the contamination from the galaxy, right?
You cannot get rid of. You just, I'm telling you in a minute what we try to do to get rid of the spectrum of the underlying galaxy.
Okay.
But if you don't have enough frequency or wavelength coverage, you cannot do so, because you have to deal with a model of the underlying stellar population. But I'll tell you in a minute. So what we did with the emission lines was to make a multi-Gaussian fit to all these lines, and try to understand what the results were telling us. And in fact, we found that the two components, this narrow component and the second component, were necessary to explain, to well reproduce every nuclear spectrum. And in fact, the narrow component could be explained as coming from the rotation, so the general rotation of the gas around the galaxy. They were normally spiral or L-type lenticulars. And this is a velocity dispersion here, and this is a velocity. So when you make a plot like this, it means that if your points are placed in this region, the velocities and velocity dispersions can be explained as coming from rotation. But when they are in this region, they cannot be explained like that. So in fact, mainly in that region here, all the points there were showing the hints of having outflows. And in fact, 1/3 of them were showing the presence of outflows. But this is just one slit through the galaxy. So imagine, and that's the central region. Imagine that you are, you have a bad scene, so you're mixing more hosts, and you are diluting the emission lines, or that you put your slit not through, for instance, if we see here, imagine that you put your slit in this direction because you don't know that the outflow is coming this way. Then you're not going to get any information on the outflow because you're completely wrong. So the good thing to do is to get integral field spectroscopy, which means that for every pixel, for every spatial region that you're covering with your instrument, you will have a spectrum for every of those. And then you will be able to understand, to trace if there's an outflow or not, and you are not depending on your chance of passing your slit through the very precise region. So that's what we did for a prototypical LINER, which is NGC1052, which is in the southern sky. So we got data from MUSE with the VLT and from Megara with GTC. You see, this is a very boring galaxy. This is a kind of elliptical or something similar to an elliptical galaxy. And the region covered by MUSE is this size. And well, in fact, this is a continuum images with MUSE in which you could detect many point sources and even extended sources. These two are higher redshift galaxies. And we did this study because of the prototypical kind of NGC1052, and also because there were previous data, IFA, so integral field data of this galaxy, but only in the central regions, these two studies here, or in a larger field of view that you'll see in a minute, but with much worse spatial resolution. So this is a kind of a mess as a transparency, but here you see the continuum in Megara in the right and MUSE to the left. So here in this square represents the size of the Megara, which will be important because we have higher signal to noise in a specific region of the spectrum, as you will see later, to describe it neutral gas. And here you see the box of previous data by Dopita, which had, as you can see here, I don't know if you see that, much worse spatial resolution as compared to MUSE that we obtained. So here you see a spectrum, a typical spectrum of one of these pixels obtained with the MUSE cube. So with the whole wavelength coverage, and this is that Megara. And here is when you can, I don't know if you see that, but in fact, the observed spectrum is in black. And you'll see that there's a red line. Do you see it? It seems to be exactly the same one, but it's in fact, this is the model of the stellar population. So we fit a model with PPXF, a fit of we made a fit, we mask the emission lines, and we make a fit of the spectrum of every pixel. And we reproduce the stellar population, then we subtract it, and then we are dealing just with the emission line spectrum, as I will show you in a minute. So here, in fact, you see that what you find from since you know the redshifts of all these absorption lines, you can have the information on how stars move for the whole map. So you have here the stellar kinematics, and here you see that the galaxy rotates. These are positive velocities, about 200, and about minus 200 with respect to the center. So you have a whole rotation in this direction that I will plot later on as the major axis of rotation. Okay, so you see the central region here, and this is the velocity dispersion calculated from the width of the absorption lines. And here's the kind of results, a normal result for this kind of galaxy when you have a peak of the stellar velocity dispersions in the central region. And this is important because we use that to subtract from the whole map, and just we deal with the emission line spectrum. So here you will have this kind of spectrum for every pixel, this one, which is the result of subtracting the stellar population to the whole thing. And then we make the same kind of multi-Gaussian fitting to the emission lines. The spectral resolution is also very good, so we can deal with that. Here you have an example of MUSE. CATs in different lines. Here you have H beta, oxygen 3, oxygen 1, sulfur 2. And here you have Megara. Since the wavelength coverage is different, we are dealing only with oxygen 1 and this red part of the spectrum. And we make a multi-component fit in which you can see the two components in green and blue, and also a third component in pink. And here in this one, you can see also the need of the presence of a very broad light blue. I don't know if you see that because it's a bit of a mess with such many components, but this is the broadband region. So we detect the broadband region in this galaxy as well. And so we will have maps of fluxes, kinematics, so in the sense of having both velocities and velocity dispersions from the lines, and also excitation calculated from the line ratios, as you will see. And also we have maps for not only for the ionized, so the emission lines, but also for the neutral gas coming from the sodium D absorption line. So this is just one example of one of the lines, oxygen 3. These are the maps. So you see the velocity dispersion and flux for the oxygen 3 line of the first component, because we find 3 components. So here you have the first component and enlarge the central part here. I'll tell you in a minute what it means, every line here. And then this is the second component. So you see the morphology and the extension. This is just a very central 5 seconds. And this is the whole about 180 seconds, and then the central parts. So these are the main 2 components, 1 and 2. The third one is only found in the very central unresolved region. So we are not dealing with that anymore because we cannot know exactly where it comes from. And here you see these are this is the region, this is the enlargement here, and this small square corresponds to the Megara field of view. This is the major axis, calculated from the stars, so from the stellar kinematics. And this line here represents the extension of a radio jet that this galaxy hosts. A very well elongated extension in radio frequencies following this position line. So we use all this information. I mean, the information is not exactly the same for every line. In general, they correlate quite well, all those except in oxygen 1, which is much more influenced by shocks and where the velocities are higher. But in principle, we can explain things in a coherent way, as you will see. This is the neutral gas. This is the spectrum in the region of sodium D line. This is a doublet in absorption. So from this spectra, so this region of the spectrum, for each spatial region, so for each X-pixel, which is what we call the pixels in the integral field spectrometers, we calculate, again, velocities, velocity dispersions, and fluxes. So this is for the absorption, which traces the stellar component subtracted. So this is why you have a mask here as well, because there may be a contribution from stars as well. So the subtraction may be not that good. We don't take into account that. And here you have the equivalent width of this absorption line. So this is the map that you have, in which we are not able to trace 2 components. We are just dealing with, the data are not deep enough to need a second component to explain the spectrum we have. But anyway, the velocities and velocity dispersions are coherent with such kind of a cartoon model, which is very, very weird. This is an amplification of the central part. So just to make you know, since we have been working with this galaxy so much, for me it's clear, maybe not for you, but just for you to have a reference, this line is what I'm trying to represent in the cartoon, where you see that the velocity dispersions is a kind of a butterfly shape. The velocity dispersions are much higher, so we can explain that in terms of rotation or whatever. And so the cartoon refers to this region here. This is the butterfly-like region, and this is the whole extension where the first component is. So in fact, we see stellar rotation along the major axis. And we see blue velocities here, red velocities there. So in the inset here, we plot also the velocities in the inner parts for the second component, which is in this direction, which goes along the radio axis. I mean the axis of the radio jet. So what we think is happening in this galaxy is that you have a radio jet which is going in this direction, which is pushing. So the outflow is traced by this secondary component. The outflow is produced by the pushing effect of the radio jet, and I'll give you some numbers later on. And this pushing of material produces all this kind of expanding bubble in a direction which is almost perpendicular to that, and that we see in the primary component, which is a narrow component. This is, in fact, the numbers that we are calculating here to try to find out what could be the origin of this outflow are given here. From luminosity in H alpha, which is of this order. We calculate the ionized gas mass, which is about 10 to the 5 solar masses. And from that number, we calculate the mass outflow rate, which is about 0.4 solar masses per year in that region, and the kinetic energy of the outflow as well in the ionized gas, which is about 10 to the 53 ergs. And also the power, so the rate of the energy of the change in energy with time, which is about 10 to the 40 ergs per second. If we compare that with the energy coming in principle from the AGN, because the radio jet is known to be coming from the radio jet, it is 2 times 10 to the 58 ergs. So the energy of the radio jet is large enough to be producing this kinetic energy in the outflow. And also, if you consider the volumetric luminosity, which is of the AGN, which is 10 to the 42, almost 43 ergs, it is, it's ergs per second. It can explain as well the power that we have in ionized gas. Nevertheless, if we consider the energy, the kinetic power that supernovae are producing because of the star formation, which is very low in this galaxy, it's about 0.09 solar masses per year, what we find is that the kinetic power from supernova would be 10 to the 40 ergs per second, which is not enough to produce the 8.8 that we have in the outflow. So we think the radio jet is producing this outflow that we see. And since we see, I haven't shown that, but we have also used the PPT diagrams for each of the regions in the galaxy to know what the physical origin is. And we end up knowing that in the central regions, we have a mixture of AGN and shocks. And in the outer parts, we have just shocks. So we explain that as coming from the effect of the radio jet that we don't know to explain, whose origin, and we don't know to explain as in the other cases of AGNs.
Isabel, sorry, can you go back to the sketch, the big one? Right, so you have the galaxy oriented like that.
This is just don't see it, that one, because this is the sketch is this part.
Yeah, right. So you have the galaxy oriented like that, and then you have this other component that is perpendicular, rotating perpendicularly to the galaxy, right?
In fact, it is not. What we think is that it is not rotating. It's a kind of a bubble that is produced in this polar direction, so perpendicular to the plane of the sky, but it is produced by the outflow, which is going through this way. So this outflow pushes away all the material that it has and produces a very, very, it's in this way. So the outflow is producing this way by the radio jet, but then at higher scales, it pushes material outwards through the region of the sky, which is easier, which is perpendicular to the plane of the galaxy.
But these blue and red velocities that you see are really like high velocity, so it's rotating.
This is the plane of it. These are stars.
Blue and red velocity, up and down.
Yeah, this is gas. This is ionized gas, which is going out from the plane of the galaxy.
Okay.
In a bubble-like structure. So in this region is where we see shocks mainly, whereas in this region is where we see both the power of the AGN and the radio jet.
Right, so it's going perpendicular, but somehow towards the direction a bit of the.
We don't know. We don't know how it works in 3D, but we think it's perpendicular to the disk of the galaxy here, and then it's through the small jet in the central region, which has nothing to do with the plane of the galaxy, but at larger scales, the material is pushed in the less dense direction. Right. Good. So, conclusions for this object, singular objects. This is very, very frequent in astronomy to extract conclusions for just one object, right? And so I'll tell you something more later on. So one of our conclusions that in fact, this galaxy is not an elliptical, it rotates. You've seen that in the stars, so it's much more lenticular, so there's a disk. This is new in this paper, and also the star formation and post-AG based stars are excluded for explaining the line ratios we have. The primary component is the coupled from the stars, and it's going through polar direction. The secondary component is the butterfly shape, is an outflow along the radio jet, and it's a tentative result on outflows also in neutral gas, but we need much deeper data. So this is a clear example of how integral field spectroscopy helps to understand what is happening in a galaxy. So we absolutely need that. So what's the problem? We did the work through long slit, that we know it's not enough. We made this with imaging, and it's not enough either because we needed kinematics. So we made just one case here, NGC1052. We are doing a sample, small sample, because IFA's integral field data are very, very, very expensive in terms of exposure times and telescopes. So we are doing, this is a work in progress from Laura's thesis as well. So we have a sample we are analyzing right now, but we, at the same time, we were dealing with some kind of pushing the imaging results. So making an atlas of doubling the number of galaxies in terms of being able to obtain how the ionized gas is distributed, that could in such a way that we could use images to select the best objects to be observed with IFEs. Because otherwise we could just try to observe a galaxy which doesn't have ionized gas in an extended region, and it would be a waste of time. So this is a work that has been already accepted. In fact, we deal at the same time with the 32 galaxies from our work, previous work from Masegosa and 11, and also several ones by Poggi, and together with new data, 6 from HST and 32 from the NOT telescope in the Canary Island, which has a beautiful spatial resolution. It's one of the best coming from ground-based data, in order to make the largest atlas to date of ionized gas. We know that it's not enough, but it's starting point. Okay, so these are the kind of galaxies we have in our sample, and as I told you at the beginning, the outflows may be detected or at least glimpsed or hinted with imaging techniques. And this is the case of NG3, again, NG34438. In fact, these colors means that we are already dealing with the IFS data, but I'm not showing you here. And this is NGC1052 from the previous results as well. So, no. So, what we did was just, most of the sample, the majority of the new galaxies in the sample were coming from NOT. And I'm skipping this, but just to tell you that the background subtraction needed a very careful method because of the filters. The narrow band here in the NOT bands don't mean, as we say in JPass, we say narrow as 100 and something. Here it is 40 something. So this is really narrow. And it's quite a complicated process, so we made a dedicated task to subtract the background. And here, this is just for you to see. This is the width of the filters. So we select the narrow filters centered in H alpha at the redshift of each galaxy, and it means that there is a contamination from nitrogen 2 as well, but it's the best we can do. And we end up with having this kind of continuum subtracted, because just for you to know, when you make a narrowband image of a galaxy, in the same image, you have both the flux coming from the line, but also from the underlying continuum. So you need to have also a continuum image in order to subtract it and to have just pure line emission. So that's a quite long process, but we classified objects considering the morphology. In core halo, this halo, bubble-like, and dusty, instead of naming as outflow candidates in order to avoid confusion, we call them bubble-like. And these were then clear in terms of being galaxies that we didn't agree among the different classifiers. And what we found is what we see. These are examples of the different morphologies: the core halo, the disk, the bubble-like example, or the dusty. And these are the numbers. So 29, almost 30% core halo, 62% bubble-like, so same kind of percentage that we already found in 2011. But in fact, what we did in this work, this is a kind of an unclear, I mean, what the numbers say is that 60 out of 70 have kinematic information, because we were interested in knowing if there was some kind of data on the outflows from what it really helps, which is kinematics. So we looked for the kinematic information in the literature, and we found 34 with data from IFS, a different, sometimes from molecular gas, sometimes neutral gas, sometimes the ionized gas, and 26 from long-slit spectroscopy from our own work. So we dealt with numbers. In fact, I'm just skipping all these details just to say that at the end, we ended up with outflows being found in 1 out of every kinematic outflows in 1 out of every 2 liners in the nearby universe. And this is how the numbers behave concerning the core halo, bubble-like, disk, dusty, or unclear. The numbers here are small, so I will be talking mainly about these regions, in which you see that the detection of kinematic outflows are in almost half, 50% of a sample, excepting for these disk-like objects. Most probably because when we are dealing with disk objects, it's because we are seeing them face on. And if you see in general, if you have a disk face on, the outflow will be coming in the perpendicular to the disk, so you won't be able to see it morphologically. That's why we don't have that kind of, and even kinematically. So this is about 55%. And I'm skipping this. We also considered the information coming from hard X-rays, but I'm skipping this. And the main thing is that morphology is very similar, but there is not a connection. There doesn't seem to be a connection with the outflows, with the kinematic outflows. So just to end up with all I have been talking about, I think I've shown you the importance of the prototypical LINER study with even integral field spectroscopic data in NGC1052, where the importance of the outflow and the impact it has in the galaxy is huge. Then I've shown you that about 50% of liners have kinematic signatures of outflows, and the probability of about 55% to find an outflow coming from the morphological information. So it's quite risky, but at least we know that 1 every 2 will have an outflow, even if morphologically we think it could be something different. Then I skip the results on soft X-rays because I didn't explain. And then, of course, the main conclusion is that we need what we are doing, the work in progress, which is to analyze a larger sample of LINER galaxies that seem to host outflows from the morphology of H-alpha, but with the integral field spectroscopy. And that's all.
Questions?
So you mentioned that I guess this is a high fraction of outflows for this population of galaxies for liners. Is this the same fraction for other types of AGN? It's lower?
In fact, it is a lower fraction as far as the other objects are studied, because normally it's said that almost every higher power AGN hosts an outflow. But in fact, there are not that many studies in the local universe. There are many studies in the a little bit higher redshifts concerning large samples, but in the local universe, it has to be precisely done. But in fact, it seems to be a lower fraction.
A lower fraction than usual in LINER.
Than in higher power AGNs.
I have a super stupid question.
Questions are never stupid.
So you said liners are low power AGN, basically, and this goes with the mass of the black hole. Or not?
No. In fact, liners may have very big black holes. It goes with the accretion rates, the Eddington ratios. So liners seem to have. they represent the low accretion rates in the.
So even not supermassive black holes can be active. So even not very massive black holes can be active.
In general, not taking into account liners, the percentage of galaxies having an active galactic nucleus is 10%. So it means that most supermassive black holes are not active. Or otherwise, during the life of a galaxy, most of its lives, the supermassive black hole is not active, as it is the case, for instance, in our own galaxy. We have a 4 times 10 to the 6 solar masses black hole in the center of the Milky Way, and it's not active now.
I asked them that.
So yeah, thank you very much for the talk. And well, I have a question I'm a bit embarrassed of asking, but since you were so nice, I mean, I will ask you. And you explained so well.
The problem with the question is that they are never stupid answers, maybe stupid. So,
so I was thinking about it's more general than maybe the like specifics of the liners, but so it's about the torus. So like we have like these big torus around like these supermassive black holes, but I was wondering if you can find some similar structures around lower masses black holes, like black holes in binary stars or things like that. Is it a matter of mass? Is it a matter of environment? I don't know. I really don't know.
Neither me. And I forgot to tell you that we have done many other things. I mean, different other things with liners as well, and studying that question, the question of the torus in liners as well, coming from mid-infrared data and comparison with models. And what we know is that even if the black hole is massive, then some things happen differently, and to explain why the Eddington ratios are much lower. And at the same time, it seems that the torus is disappearing as well. So I don't have the answer to tell you what it happens or how it happens, but the unified model is not as simple as I've shown. So there are other dependencies. One is the accretion rate. And with respect to the mass, we don't know. We see that there are 2 phases in binary, in X-ray binaries. There are 2 phases that we try. One of those we try to connect with X-rays, with AGNs, but it's not that similar in some respects. So I don't think there is a torus in binaries, and the torus has been invoked in AGNs to explain the different types we see. We have hints of having access to the torus itself with recent data from ALMA, and from data from the near infrared. We don't know exactly if it is in fact a torus itself or it is a dusty outflow going perpendicular to the disk. So I mean, these are kinds of simplifying assumptions to try to understand how the general things behave, but when going into the details is much more complicated than that.
Thank you.
Okay, so first of all, thank you for the very nice talk. And I had a question that regarding the future work, what I understood is that you want to extend this analysis to other LINER objects and see statistically how this outflow behaves. So the question is, do you think that with this statistical sample, would you be able to conclude or say something about how the outflows in general, not just in LINERs, favor or not the star formation rate, or how this expelling of material creates more star formation? Or
first of all, I forgot to tell you, I think I wrote that, but I forgot to tell you that the LINERs we are analyzing are non-interacting objects. Because when we put together interaction, then I mean, it's a mess because you don't know what is happening. And because star formation has been enhanced, greatly enhanced in interactions as well. So we try to get rid of other possible origins for explaining outflows and looking into LINERs first, because it's easier in the sense that you have a much bigger population in which you can then try to bin the properties because you have large enough numbers in the local universe. It's expensive in terms of exposure times, so telescope time. So we will have a sample. We won't have just one object, but we are talking about 1/10 of objects. So of course we will have conclusions. How they can be extended to the whole population of LINERs in general and of AGNs even more general. I mean, we have to deal with the kind of data we have, and we have to leave room for next generation astronomers, right? Now it's low. It's a low work because we need a lot of data, and of course the results will be. I mean, we've been always said from when the times in the last century when I started my PhD that the research gains a lot from making huge samples, statistically representative and everything analysis, but also from the very, very detailed studies of small samples, because they have to be small because they cannot be otherwise. But I think we need both approaches.
Maybe one last question and then.
Yes, maybe one more for now. So you investigated the jet shock induced bubbles, right? And this type of outflows. Maybe there are outflows from the accretion disk or from circumnuclear disks, like other types that are not included in LINERs. Like, are there different mechanisms of producing such outflows other than jets?
In fact, in star-forming galaxies, outflows have been also found. So huge star formation production produces also outflows. So in fact, we have to, I mean, we try to conclude, I mean, to find a conclusion on what the origin of the process was seen is. And in this case, LINERs are not forming stars at huge rates at all. They are not star forming by far. Star formation in LINERs is quite low. So again, this allows us to get rid of that process as contributing to the whole thing. If you take into account galaxies in which you have strong star formation and you have strong AGNs, then the situation complicates it. And then you have interactions, so you complicate things. The question is to try to understand the whole multi-frequency information we have on the objects. In Seyfert galaxies, you normally don't have radio jets, so you have to deal with other explanations. The question is what the origin of the radio jet is much more profound. But I mean, just trying to look for connections between the features you see in LINERs, for instance, the percentage of galaxies hosting small radio jets is higher than in Seyfert, much higher. So in this case, outflows may be related. And we need to find out how jets are formed in these galaxies and how they relate to the rest of what we see in them.
So I guess I know. So the question is if these kind of things could be studied in simulations. I mean, I guess not in super cosmological simulations, but in more specified like things to understand these kind of things.
Of course, there are many very, very detailed simulations of tailored simulations of galaxies. In fact, there's ones for NGC1052 to try to simulate how gas is moving and how you put a jet and how it goes through the galaxy and so on. And by now, simulations provide much more information than what we can have because we are dealing with projections as well. So I mean, it's not easy to make the direct connection between the simulations and the observations we have, as it's always the case in astronomy, because we cannot get there into the object and then move it. Okay, but things are progressing quite fast as well from the point of view of simulations. And in fact, that's what we need to do then, just to try to find out. I mean, this is we considered the simulations for this galaxy as well, but we didn't do them. We just, tested, whereas the scenario we were invoking was sufficiently inclusive within the simulations.
Okay, I think we need to wrap up because the reservation also, many of you are going, it's should be there at 1:10. Okay, yeah, that's when it was available for many people after they're busy at the Lucas, guys, where it is. Okay, so nothing. So thanks a lot, Isabel.
Thank you.